Good morning, good afternoon, everybody. Welcome to AABEA's technical webinar session. AABEA stands for American Association of Bangladeshi Engineers and Architects. আমরা প্রত্যেক মাসে এই একটা করে করার চেষ্টা করি এই প্রোগ্রামটা, এবং প্রত্যেক মাসেই আমাদের একজন করে আউটস্ট্যান্ডিং স্পিকার থাকেন, কোনো সময় প্যানেলও থাকে। So today we are very fortunate to have Dr. Nazma Ferdous. উনি নাসার সঙ্গে দীর্ঘদিন ধরে স্পেস টেলিস্কোপ এবং এগুলো নিয়ে উনি কাজ করছেন, and she will give a talk keynote. So without further ado, I will ask Shahida Abdin, the current president of AABEA Washington DC chapter, to introduce the speaker. Shahida, please unmute yourself. Shahida, আপনি আনমিউট করেন, আপনার কথা শোনা যাচ্ছে না। হ্যাঁ, এখন শুরু করুন।
Can you hear me now? Sure. Okay, thank you. Hello and good afternoon, everyone. I'm super excited to have you here with our AABEA webinar series. I'm also excited about the conversation we'll have today. We have an amazing scientist who will be sharing her stories of journeys with us. When I say amazing, I mean it. She is an action taker. If you listen to her stories, you will notice that different stages in her life, she said yes, and she did paid off her ambition. Her story of journey will help you to go to from good to unforgettable. The amazing Wonder Woman is Dr. Nazma Ferdous. So I'm going to give her little bio today. So please stay with me. Dr. Nazma Ferdous is a principal software engineer in the Astronomical Planning and Support branch at the Space Telescope Science Institute, STScI, in Baltimore, Maryland. The STScI is operated by operated by Association of Universities for Research in Astronomy. She has over 22 years of experience at STScI and has worked on the design, development, and maintenance of planning and scheduling subsystem for the Hubble Telescope, the James Webb Space Telescope, Chandra Space Telescope, and upcoming Roman Space Telescope. Dr. Nazma Ferdous was born in Dhaka, Bangladesh, and Dr. Nazma got her BTech in Computer Science and Engineering STScI from Indian Institute of Technology, Bombay, IITB, in 1996. Later, she earned her doctoral degree in Computer Science from the Graduate Center of the City University of New York. Throughout her career in STScI, she had published technical papers in various workshops regarding her work in planning scheduling system used for space and ground-based telescope. Ladies and gentlemen, please welcome Dr. Nazma Ferdous.
Thank you, Shahidapa. Thanks for the excellent introduction. I think I've never been introduced this well, but I'll try not to disappoint you with that amount of expectation. But anyway, so I will start with my talk is about scheduling the first year of James Webb Telescope. The reason this was kind of interesting because we have been scheduling observation for space-based telescopes starting at Hubble Space Telescope and other smaller one. And when we have retooled that software for scheduling James Webb, and we try to anticipate as many things as we possibly can, yet once the operation started, there were many unexpected issues that came up. that needed to be done immediately. This was a $2 billion, $10 billion telescope. We couldn't wait, and science needed to come out. In my 22 years and space telescope, this was the time we were literally like pulling our hairs out. That was very interesting experience. So I will start with a small video of James Webb's from NASA, and then I will go into the actual presentation. I'll share my screen now.
We have uncovered wonders undreamt by our ancestors who first speculated on the nature of those wandering lights in the night sky. We crossed the solar system and sent ships to the stars. We continue to search. We can't help it. A central element of the human future lies far beyond the Earth. Crave some cosmic purpose, then let us find ourselves a worthy goal.
And I will say this was a worthy goal for sure. This was the video I was supposed to show you. Okay, so James Webb in his first year came up with many, many interesting discovery. And beautiful, beautiful images that we see. They all have, beyond the artistry of this beautiful landscape of the space, there is a lot of scientific value to it. I think the scientists would be probably more equipped to explain, but I will talk about the engineering of this observation and how this is done and what kind of problems we faced in the first year. That was beyond our anticipation. So just a few background things. The James Webb Telescope was launched on a Christmas Day, 2021. We were coming out of COVID, a good gift for all of humanity, I guess. And it took a million miles before it went to where it was supposed to rest. And it was inserted into the orbit in the second Lagrange point between Sun and Earth. And it took about a month to go there. After 6 months of commissioning, the telescope began its science operation about 6 months after, in July. And so at that point of time, the scheduling software, the planning and scheduling software SPIKE started to really being engineered, really activated. That was originally developed for Hubble Space Telescope, but it has been retooled for JWST as well. We review the process of observation planning and scheduling flow for HST as well as JWST, show that how this approach extended for HST, for JWST as well. And we also highlight the challenges that we faced in the first year. So this is a little bit background about what is STScI. It's a science institute that is located in Baltimore. And the goal is expanding the frontier of space astronomy and just increase the knowledge. That's the main goal. And this was contracted by NASA to run as a science operation for Hubble Space Telescope and later on James Webb. And in future, it will also be operating the Nancy Grace Roman Space Telescope as well. That is supposed to be launched around 2026. It has about 800 staff members, Many of them are astronomical science people. There is a public outreach portion of it. That public gets to know what is what's the frontier of science. And there is a engineering team as well. Out of that engineering team, there is a data analysis, which is probably post-operation. Once the data comes from the telescope, that's their job. There's a flight engineering group, but also this observation planning and scheduling team. That's what I'm part of. And that particular team has about 65 people that does all the software development, operations, and so and so. So this is a lifetime of a proposal. How this happens, it starts from the science community. Initially, the call for proposal goes in, the astronomer submits their proposal that has to have good scientific justification for it. And this gets reviewed by the PR, their PR, and depending on the scientific value of it, some of the proposal gets chosen. It gets timed on the telescope. And once the selection is done, then this proposal that was originally in paper becomes, the data gets put into the database. And once that happens, once the proposal gets constructed in data, then the observation planning team comes along. It takes all the proposal for the year and try to figure out what is the most optimized way of doing that, laying this out throughout the length of the year. And then once that planning happens, per week, there is a scheduling team that will look into this plan and figure out what are the things that will actually get on board, what are the observation, and they will send specific command that will get uploaded to the telescope. The data gets captured, the data gets downloaded. Once the data is downloaded, the data analysis group comes in and they will do the post-processing. They will put things into archive and give it back, the data, to the original PI. The PI will have it for 6 months exclusively and do all the research that is needed out of the data. Once 6 months is over, this data can be accessed to anybody in the world. And out of them, many paper comes out, the science goes back to the science community. So this is just another way of saying the same thing, that science program gets the program definition, the selected program gets the program definition, then we calculate all kinds of constraint over it. So every observation obviously is in a part of the sky that may not be feasible for the whole year. You cannot directly look into the sun, you cannot directly look into the moon, you cannot even directly look into the earth, because all this optical instrument is extremely sensitive. And they're trying to really capture very faint light from the edges of universe. So anything bright, it cannot really look at. So you really have to pull it away from anything bright and try to look into the very faint light. So there are many constraints that you cannot look this way or that way. And of course, the telescope's mirror, primary mirror, of course, have certain amount of degree of freedom to move. It can move like 5 or 10 degree either way, but not, it doesn't have a 360 degree movement, freedom of movement. So you'll have to calculate all kinds of when this observation is actually feasible during the year. And once that happens, then the SPIKE long-range planning team comes along and we figure out how to most optimally do it throughout the year. And then once we give them certain amount of plans, and I will explain what that plan means in a next slide, then the short-term scheduling is created out of it. Short-term schedulers are really talking about which observation is to go when, and every observation will have to actually direct to the pointed to that star that it is trying to look at, and how does it move and slew it out and so and so. So it's a little bit more detail on every observation, that short-term scheduler, and that comments ultimately gets uploaded to the telescope. So the SPIKE software that I work on is a planning and scheduling software that's used for the space-based telescope. We have also used it for ground-based, but mostly from space-based telescope. Originally, this was developed for HST, and then once we realized that JWST and other space telescope, given that HST, the Hubble Space Telescope, was actually a huge success, the astronomical community decided that we should put out more telescope in the space to try to really see this faint light and try to see at the edge of universe. So at that point of time, rather than redoing another software, we have decided that we are going to retool this software for JWST as well. So at that point of time, what we did is we took that software, we created what is called a generic part of it, because there will be some astronomical utility of it. There will be domain models of it. Domain model would be like, how do you define the observation? What are the constraints? What kind of targets that we are looking at? And what are the how do you actually look at what are the constraints looking at the target? That would be the domain model. And the planning and scheduling model would be, well, I have all the feasibility window. What is the heuristic that I'm going to use it to best optimize the time in the telescope? So what we did is we kind of created a plugin system. We created a generic version of a scheduler, and where everything can be really plugged in the sense you can define what are the new constraints, what are the new type of observation. You can define what are your heuristic and how do you want to optimize it. And that really enabled us to create a specialization for Hubble, created a specialization for JWST, and created a specialization for Chandra as well as Roman. I will mention here that most of the software that is used for NASA missions, and NASA missions are really, really good for coming up with very good hardware. When it comes to software, they are a little shy because you really cannot have a software bug on a $10 billion telescope. In planet Earth, software's bug happens, you can change it, you upload again, patch happens, you can solve the problem. But something which is very expensive, far out in the space, the operators and mission specialization people, they are very, reserved about using software. So most of the time, the usage of software is not as good as you can have. It's really very conservative, let's say that. And most of the time, they really tune it for that mission. Spike is one software that actually lived on for more than 30 years now. And the reason it really lived on that, because we really created this generic version of it where you can plug in and out depending on your mission. Now, people who studied computer science, that would be very obvious to them. Like it will be a very interesting thing to them. How do you really come up with the abstract generic version and specialize things rather than redoing software over and over? And that's what we were able to do in this case. And this software lived on for more than 30 years and used in many, many missions. That's not, that's a very, that talks about a lot of legacy of Spike, and unlike many, many other software that are used in NASA mission. So this is a graphical user interface of the software that I was talking about, and each row here basically represents one observation, and the blue rectangles are where the feasibility windows are. You can see the timeline on top, and this is where the blue rectangles are showing the feasibility of that observation that can be done. Rest of the time you really cannot. So this is just example of a few constraints. You have to avoid the moon and Earth, and of course the sun. Sun is shielded using the sun shield of the JWST because it's too bright. And there is a field of regard. How much can you see? Which direction can you see? What is the degree of freedom to move this primary mirror? You also have to have guide star because you are again trying to see very faint light. So in order to really fix your your gaze in a certain direction, there are known bright stars that space telescope use to lock in that direction. You of course have other type of constraint, like observation 1 needs to happen 10 minutes before or 10 days before observation 2, and so and so they must happen in certain angles. Observation 1 needs to happen 30-degree away from observation 2. There are all this relative constraint also, but main point is we calculate all this constraint, relative and just the absolute constraint on that particular observation, come up with what the feasibility window is. So this is just the feasibility window, and next slide will show out of those feasibility window, Spike will come out, give you a plan window. So the plan windows are basically a subset of this feasibility window, which we call it constraint window. But why a window rather than a time? The reason behind the window is the telescope exact location cannot be calculated to the minute and second until last week or so. The exact location of the telescope is not known. We have a model. There is certain, within a limit of certain uncertainty, we can say that it will be around this place, but not exact location and time. So that's why we have to give them a window for this observation to happen. And it's a least commitment window. So we kind of say, and these windows tend to be 56 days. And within these days, it will happen. We'll try to make it happen. That's the idea of the plan window. Then next, what happens is these plan windows are used to distribute when this observation will be taken throughout the year, take into account that times are well utilized, take into account that we are not overburdening the recorder for data. We are make sure that the difficult ones that generally has to happen short burst of time. There are some observation more difficult than others. They might have very high data volume. We are not pulling them together. We are distributing them over the time period and so and so. So it kind of creates a stability for when this observation has to happen. The other thing about the plan window is the PI gets to know during this time of the year, my observation will be done. So he or she can hire graduate student accordingly and do the necessary simulation and research accordingly. So we create the plan windows, and they kind of look like this. Within the feasibility subset of the feasibility window will be our plan window. Once these plan windows are done, every week, what they do is they'll figure out this. Then the scheduling team comes in. The scheduling teams for every week, it will figure out which observation have plan window that straddles that week. From that observation pool, it will try to choose which observation might go that week, and then create necessary command for actually doing that observation. So it has a two-step approach. So the long-range planning that Spike does actually assigns observation least commitment plan window for 56 days. And what we are trying to do here is create a stability of the plan. We want to do the resource balancing. We want to really optimize the timeline and make sure the best usage of time happens. And the short-term scheduler, what it will do is it will week by week, it will create second by second scheduling for doing actually executing those plan windows as input. So we have a two-step approach. And as I said, mainly because exact time, exact ephemeris is not known from before, unless you come very, very close to the timeline. So the roadmap of this talk is we will talk about what are the problems. So up until now, I kind of try to give you an overview of what Spike does. Now I will talk about what are the problems we had during, we did not anticipate after the telescope came into operation. And some of them are that we needed to recalculate the constraint too many times, or there is a micrometeoroid avoidance and link observation and so on. So I'll go through each one of these in a little bit more detail. So the first one was a constraint parameter. So what happened was during the commissioning period, the state of the telescope was changing more quickly than we anticipated. And the constraint on all this observation are calculated using various different parameters, obviously. All these parameters together, we call it program reference database. And generally the expectation was as soon as any variable will change, any parameter will change, we will have to update the constraint. So all science operation, all observation were expected to use the newest PRD, which may have some change in some kind of parameter. So turned out that you have about say 8,000 to 9,000 of operation for a year. And updating those constraints for all of them was time consuming. You really cannot do that because they were literally changing by the hour during commissioning. So what became apparent is there are many parameters, and some parameter does not really affect the constraint window or actually the feasible window. They are there for other reasons. So why are we changing our constraint for the parameter that were not affecting the feasibility window? So we had to separate that out and figure out a way so that Spike can still operate without the newest PRD, even though the constraint has not been updated using the newest PRD, we can still work on it. So we had to separate out which parameter actually affects our feasibility window and use that rather than all these other parameters that are constantly and very quickly changing. So that's one thing we had to release as a patch. The second thing that happened was, I don't know how many of you heard, early in the mission, the JWST mirror was hit by a micrometeoroid. Now, this micrometeoroid is basically a fancy term for space rock. So we have all this sci-fi movie, right, where a rock comes and hit your telescope or your spacecraft. This is exactly what happened. And we do not know how many, supposedly up till 14 space rock hit the primary mirror. And this was not expected. I think they had a model of how many space rock might hit, but this was not, this was beyond their expectation. So we had to do something at this point because we cannot be having this many hit because the primary mirror would be too damaged in that process. So we had to come up with a way to move the primary mirror away from the direction of the space rock. That's what we did. But at this point, I will add that in order to do that, move things away, that means some of your timelines or some of your feasibility window, that means is no good, right? Because I showed you those feasibility windows. And like say, this was our feasibility window. Now we in JWST, most of the time, the feasibility was not that, I mean, it was widely feasible most of the time because it's going around the sun compared to HST. JWST had much more wider feasibility window. Turns out if you have to move the telescope away from the path of the space rock, half of your or much of your feasibility window is not good anymore. But how do you do that? You have to first come up with what are the window for this collision and try to basically subtract those windows, right? That's what we had to do. So Spike, as I said, was in a very plug-in system, right? Originally, we said that we separated out. So in the domain model where you can actually plug in and out constraint, that came in very handy. At this point, we can just define another constraint saying where you need to avoid this timeline, because that's when you have the possibility of hitting the space rock is much higher. So you feed that constraint and then see what is your feasibility window, and then you go on from there. So that's basically what we did. But okay, so this is a schematic diagram of what this, we came up with something called a micrometeoroid avoidance zone constraint. Now, what this micrometeoroid avoidance zone constraint is trying to do, this is a schematic diagram of the field of regard. Field of regard is where you can see, the primary mirror can see. It tends to be at 90 degrees from the anti-sun, because sun shield is kind of blocking. And if you see the see how JWST look like, the primary mirror is kind of on the 90 degree from the sun shield. The sun shield is always looking at the sun. So the gray part is the field of regard, and this vector, if you see this vector coming out from the page, that is called a RAM vector. That's the velocity vector of the telescope. That's the direction the telescope is going right now. That orbit, that's the direction of the orbital velocity vector. And the motion of the orbital direction is about 30 kilometers per second. So it's quite fast. So the idea is, if you are actually going in the direction of the orbital vector, that's when, if the space rock hits you, the momentum of the space rock would be the highest. So it's basically, if you're going to crash into something, don't try to do frontal crash. Try to crash from the side. Because if you crash from the front, the momentum is the highest, and that's when the space rock can actually damage the primary mirror. It has the highest amount of force that it is hitting with. So that's what it says here, that momentum of incoming micrometeoroid would be enhanced by the observatory motion. And that will increase the risk of potential damage. So the idea is, don't look directly at the velocity vector, look around. And that's when you avoid the impact of the micrometeoroid. So the zone here on the second picture, the red circle is defined as the half cone around the orbital motion direction. Try not to look in that. That was the point, look around as much as possible. Now, turns out, if you try to do that, targets that are closer to ecliptic plane of that orbit, half of your visibility window just no longer good. The ones that are more north or south to the ecliptic plane, the target, most of it, visibility window remains visible. So this is a two-dimensional diagram of how the micrometeoroid avoidance zone cuts into your visibility. If you're closer to ecliptic plane, you can see half of it is no longer good. If you're more closer to north and south pole, then you at least 2/3 of the visibility still remains. So that was the study that we did. We basically fed in that constraint, and then we figured out, if you look at this graph, the X direction is basically number of day with a number of day. This is kind of say number of day without mass impact. This was our original visibility window. And Y directions say, if you completely show that impact, meaning take away the day that are no longer, that are in the mass area, meaning only give me the days that are outside the avoidance zone, then you will see almost half of them, I mean, most of them loses 50% of the visibility. About 15% of them loses all of the visibility. Some 15% of them more or less keep the same visibility. That was the study that we came up with. Okay, that was the study that we had. So what we did is we quickly was able to fit in this constraint, tell the engineering team that this is how the new feasibility studies would look like. And you can imagine that some of the plan windows were no longer legal at that point. So the operation team had to completely redo those plan windows. And that's what we given them that choice. And turns out in cycle 1, when original proposal call was asked from the astronomers, there are certain proposal, if you don't use the mass, if you avoid the mass area, then they are not feasible anymore. But some of them had high scientific justification. So the team had taken a calculated risk at that point of time, that if there are scientific justification for it, and without the mass area, we really cannot do it, we try to go around it, meaning if I go back to the original picture, you can see in that red half cone, some areas are worse than others, meaning the area right around the RAM vector is the worst, obviously. As you go from the center of that circle outward, again, the micrometeoroid heat will be less and less direct. So can we have a few days that are outside on the kind of skirts on the surface of this red area, and mostly away from that center of that velocity vector. So try to be away from the center. So how do you do that? You can create a heuristic to do that. The way you do it every day of the plan window, you see how far from the center it is. You use that heuristic, come up with plan windows that are slightly outside the center as much as possible. So we given them a new constraint, we given them heuristic depending on how far we are from the center of this velocity vector. And during the cycle 2, which was the next year's proposal list, this is a diagram of how the resource look like. The first picture shows, if you don't care about mass, how would they lay out? This was a distributed way. This is how the resource on the timeline looks like. The second picture shows that if you say no mass at all, meaning you cannot really schedule something at a avoidance zone, then you can see later half of the year, it becomes more empty. The first half becomes more front-loaded, too many proposals to do. And if you kind of go in between, meaning things that cannot really, the proposal that are not feasible in the mass area, use a heuristic to go go as far as possible from the center of velocity vector. Then you get some of those feasibility windows. It gets a little bit more distributed, but it still has a lot of hole in this area. So at the end, I think the operation team chose between the hard constraint and the heuristic. So use the hard constraint where you can. If you have scientific justification, then use a preference. If you really, really have a scientific justification, you have to really crash head on, do that, but make it fewer and far between. That's what I think they went, and try to distribute the timeline as much as possible. So this was the micrometeoroid stuff. Next problem we had, now our constraint models were coming out of HST, and HST is an orbit-based telescope. It's an Earth orbiting telescope, and everything is in the orbit. Every day it has 15 orbit, and almost half of the orbit almost is occulted by Earth. I mean, because it's going around the Earth. So what normally happened is any kind of non-science activity, meaning where you are not actually capturing the data, you are positioning the telescope in that direction, or you are trying to update trying to do something with the instruments and so and so. All those engineering activity, which is not science activity, were done at the Earth occultation period. And capture the guide star and so and so. All those things used to happen during Earth occultation period. And when the telescope came out of the Earth occultation and can directly look into the target, that's when you capture the science data. For some reason, say this failed, for whatever reason, the guide star could not be found, the scientific instrument is not up, or whatever the reason, if for whatever reason it failed, rest of the time in the orbit was just wasted. because everything was fragmented for orbit. Everything needs to happen in orbit. JWST, on the other hand, has a continuous timeline. The idea is use time as best as you can. So all this non-science activity, meaning your slew looking directly at the target and also trying to figure out the guide star, all those things has to happen in a continuous timeline. It's not at this point fragmented by orbit. So the JWST onboard has a software system. What it does is, for some reason, if observation fails, pull the next one. Rather than wasting time, pull the next one and execute it. That actually, while it is really good, you're not wasting time, that broke our constraint model. And I'll explain why that is so. The JWST observation are linked with one observation with another. Many of them are linked by temporal constraint, meaning it has a timing link between them. Observation 1 needs to happen 10 days to 20 days before observation 2, something like that. So when an observation is executed on board, the execution time gets fed into the system, and all constraint has to get propagated, because once an execution happens, rest of them gets shrunk. Rest of their feasibility window gets shrunk for obvious reason, because then you are making something stuck at a timeline. So what happened, unlike HST, in JWST, many of them were getting executed outside the plan window, because once something failed, the system, onboard system, decided to just execute the next one. Now, at this point of time, our propagator failed. I mean, I'll give you an example. Say observation 1 needs to happen 10 days from 10 days before observation 2, or so and so. So observation 1 failed. They just pulled observation 2 before it can happen. Between them, the timeline was, say, 8 days. And at this point of time, your original link is no longer good. So the temporal constraint propagator that has been in place for 30 years, worked perfectly well for HST, suddenly did not work anymore. So this is an example of how we define something called a linked observation set. I have 5 observations here, and the red lines are actually a link that are defined in the proposal by the PI. And the green one are something called a transitive closure. This is a computer science term. So this is basically says if 1 is related to 2 and 1 is related to 3, 2 and 3 is also related. That's the transitive closure. That's a full closed form of your link. So the link sets are defined by transitive closure. You take into account the link that are defined, you figure out what is the transitive closure, and that full fully linked one is your link set. So once a link went bad, say observation 1 and 2, between them was supposed to be at least 10 days. Whatever reason, it was 8 days, because most of the time the reason it happens is because 1 or 2 failed. At that point of time, all the link that are associated with 1 and 2 will go bad. And the whole link set became unsuitable. That was our model. Now, the obvious thing would have been obviously to go and change the proposal definition, go and change the link that was bad, change it to something else. But every time you change the proposal, it's a lot of work on the operation team. We needed to computationally do something, because this was happening not like once or twice, it was happening quite often. So what we decided to do is following. We decided the whole concept of the link set, we decided to put it in a container. And at this point of time, all the actual link that PI has defined was still there, but they can be actually marked as effective or ineffective. That's what we do. The bad link in this case will become an ineffective link. Rest 3 that PI had defined will still remain an effective link. Once we did that, then you drew what you did before, come up with the transitive closure, propagate the constraint, and so and so. And then this is the picture you get. The 1, 2, 3, 4 are still linked by each other, and some of the transitive closure links are still there. But 2 only is linked by 1 by a bad link. But remember that 2 at this point was tried on board and failed or something. So we don't really care about something that is already tried or failed or so and so. We really care about the observations that are still not on board, has not been executed or not attempted to be executed. So the ones that are so-called unexecuted or hasn't been tried on board are still linked with each other, and this is good situation at this point. So why we did that, because if you break up the link and so, you will actually really disassociate this member, the observation 2, from rest of them. And what it does, it loses the history, and the operation team has to go and change the proposal for every time a constraint become defunct. It was a lot of burden for them. So we try to do it computationally. But this is a good picture. The rest of the observation did not have a broken link. That is not so true in real life. Sometimes you get broken link. So this is a situation where things are actually got broken, even if you tried computationally. So what is a broken link for us is defined as 2 unexecuted observations that were linked prior to this failed observation, but no longer linked anymore. So my first picture is the picture that I had in last slide, where I conveniently made observation 2 to be the failed one. Rest of them were still linked, but say observation 1 failed, and 3 and 2 were actually linked to observation 1. At this point of time, you will have broken link between 3, 4, 5, and 2. You will have 2 components of the link set. So what to do with it? What we did is we gave them warning that this has happened, and only when the link is broken, the operation staff will look into it and decide what to do about it. And the other thing we told them, if you actually define your original link more as a chain, then what happens is, even if something fails, you're not going to create too many sparse parts. If you define something from 1 to many, like for instance, in this case, 3 is linked by 1, 4, and 5. If for whatever reason 3 went bad, 3 was failed, you are going to create all this thing completely disassociated from each other. So we kind of discourage them to create define link like that, define a link as a chain as much as possible. So even if you break, you're only going to have 2 components rather than too many components. And if there is actually a broken link, computationally identify, tell them this is a broken link and this is the failed visit and so they can actually go and at that point make a change in the proposal rather than doing it for every failed visit. So this is what we did for the broken link. The third one is a Miri greeting wheel. This is still a work in progress, so I'm not going to go too detail about it. But Miri is a near infrared instrument in JWST, and it has something called a grating wheel that goes in every direction, like go in a positive direction, forward direction for a while, and then it reverses the course and goes in the reverse direction for a while, so and so. So turns out without much planning, if you are just doing all this observation that requires Miri as an instrument, they were changing the direction too many times and caused too much excess friction on that. So at a certain point of time, they just stopped planning those observations, the operation team. So what we had to do is, okay, if that's the case, we have to really define a sequence of domain. A domain will be consisted of observation, Miri observation. The idea is each domain will rotate in a single direction for a while. So go forward for a while and then switch the direction, go reverse for a while. And so on. So the only restriction we had is anything in domain N has to be scheduled before domain N+1. So you cannot take something from domain 2 before you finish domain 1, so and so. So this is how a schematic diagram, this is still in the simulation phase, we have not done. So each one of this arrow is sort of a domain. So a neutral point is say in the middle. Now I know this is called 0.35, and why the operation staff said 0.35 should have been 0, but for some reason it's 0.35. The idea is you go one direction for a while. The yellow lines in both direction is where your preferred, you should stop here in preference. Red lines are the one you can go up until this 50 rotation, but this is really pushing the boundary. So idea is in each direction from the neutral side, you should not go, you should go about 30 rotation. 30 rotation each direction. So you go left direction once and then change the course, go right for a while, change the course, go left for a while, and then go right for a while, and so, and figure out how can you choose your Miri observation in a way so this happens. That's the idea, but this is right now simulation. We are still working on it, how that can be done. And the last one I will say, you know, these people who works in government will probably understand. Government is trying to definitely put a lot more bureaucratic stuff, like, you know, do paperwork and filing and this and that. So for HST, every time we figured a problem, we troubleshoot it, we know what the software solution is, we could do just basic software engineering, file a ticket, figure out what the solution is, do some configuration control, do some testing, and just give them the patch. Turns out in JWST, they really want to make sure the whole system is good before we can change any software at all, we can put any patch at all. And that requires a very extensive testing across the systems and so. And requires a lot more paperwork. You need to take permission from the mission office and so. So anytime a problem is identified, we cannot just give them a patch, even though we have a solution. We have to really think about a workaround. So our way of software development really went into, okay, we gave them some capability. If it doesn't work, can we do a workaround? One. And B, if it is too much, then we sometimes have to ask for permission. But this is really put some, what do I say, break into the way we think about, you know, very quickly give them patch. The one thing about STScI, because the whole institute really have the operation staff, science staff, and engineers all together in a building. For us, you know, we can really interact with the stakeholders. We don't have to go out. We don't have to come up with a meeting. It was a very smooth sailing situation because everybody is in the same place. That's no longer as true. You really have to be careful for your release, that if make sure that things work, and if not, there is a workaround. That was something we didn't really think as much before. So that would be our end of talk. These are my colleagues who actually helped in this slide making. Mark Giuliano, who is my supervisor, and Leiko Reger, she's my co-worker. So that's about it. Before I go into question and answer, I will answer your question, Nasrinapa, that you said if I'm going to talk to a 5-year-old, then what should 7-year-old, what should I say? There are actually public speaking talks in the institute, and the idea of public speaking, and we do have an office of public outreach, and I think STScI has a office of public outreach that's probably much bigger than many of the other NASA operation. The way they do it, they really, rather than going into engineering talk, they really try to like spur the imagination of those kids with the science and what are the science speaking, that the images are just gorgeous. And what they do is they use the image and try to explain what that means and really spur the imagination for there and tell them that this is not all we see. There's so much behind, so much behind. We need to really push the boundary. Our understanding is only on the surface right now. We still don't know what the dark matter is. We still don't know what the dark energy is. We still do not, I mean, we have an idea of Big Bang, but we still not sure, 100% sure yet. There are other things going on to validate that. And what happens to the universe? There is this whole anti-gravity going on that really takes the galaxies away from each other. So most of the time, what they do is they really, if you talk about the science, you almost can make it a story out of it. That will be a lot more story-like, rather than the engineering talks gets a little dry. You really can make them sound like this galaxy is playing with this, and this galaxy gets formed this way, and how the galaxies form, and how the nebulas happen, what's the timeline of a star, and when star dies, what happens. All of them are as much of a scientific value. It is almost like your a suspense novel, if you say it correctly. So that's how they try to spur the imagination, get them interested into science, get them, try to think what this is supposed to be saying. We talk about, a lot of time, this science and engineering are thought to be very dry subject, but if you really, there is a lot of art into it too. There's a lot of beauty in it too. You just have to present it. I had a physics professor who once trying to teach us what happens to the charged particle, and what happens to when the sun is bursting with it. And he really, rather than going into the equation, really tried to present it as a drama between this charged particle and how they are getting excited into the magnetic field of the earth, and so and so. And they were almost the characters of a story, and it was really presented well. And once he gave the story, then he said, okay, imagine this equation is trying to tell you a story, that all these XYZs, they're just characters here. And it just very succinct. It's like one line saying a story. Like E equal to MC squared, in my opinion, is art of work of art. It says so much. E means something, it's a character, and M and C, all of them is a character. And there is a big story, beautiful story behind it. So, we have to really, the science has so much art into it, but it needs to be conveyed. And I think that's how you capture young minds. So, okay, I'll stop right now.
Thank you very much, Dr. Ferdous. I think you explained it so beautifully. The right side of the mind and the left side of the mind, they have to come together to understand anything. So I will touch base with you unofficially later, how to get access to those children's world, and I'll let you continue your question Q&A. Thank you so much, Najma.
Thank you.
Well, we
Nasrapa and Nazma, I have something to add with that, if you allow me. Yeah, actually, I'm going back to the Nasreen Appa's question and the answer from Nazma Ferdous. Actually, NASA Visiting Center inviting young kids to visit NASA Astronomy Observatory Center. So I am working on that to, I don't know how far I can go. I need maybe Dr. Nazma Ferdous' help, because we are, I'm trying to schedule for a visiting, astronomy center visiting purpose. There is a day I want to select from AABEA. We can take the young kids to there. So actually they have some facilities there. So we can bring our young kids to, see there by their own eyes what's going on. So it will be the better idea to bring them. That's I'm planning actually.
Sure.
And Dr. Nazma Ferdous, I have a question. It's a scientific research purpose. So far, what we understand based on your conversation, that how the software are working, and some of those points really I followed, because since I'm in the hardware side. So I want to know about something Hubble mirror follows, because it said, since the rock is heating and lots of concern. So now, so since the rock noise and the diversity of corrective optics, So do you have any data for the new tandem of optical glasses? Because it's hitting the glasses. So because if it is the tandem from outside, even though it's hitting the rock hitting the glasses, the tandem optics will give enough information as long as they can correlate with this tandem to the telescope. Let's say one rock is destroyed, and but tandem is corresponding to give the optical data. So in that purpose, they're not losing anything. That's my understanding. Are you working with that? Like
I am not, but this is what I understand. When the rock hits, there are two things that happens. The coating might get damaged. The other is you can have a very, very, very tiny small dent, which is a bigger problem.
Yeah, so that's the dent and whatever. That's I said rock noise, right? Rock noise means they might damage it or do something. So in that purpose, if we have correlation with the space-borne tandem optics, so they might get the optical result. I think they're working, but
I mean, there is a way to correct it. Once there is a dent, you can actually correct it. But the thing is, if you look at the primary mirror, it's a large football field size mirror, right? It's taking all this light, very, very faint light, and trying to concentrate them. It's possible that once it comes down by the downlink, you can try to change, but on board, all this light on this football field, they are getting concentrated, right? And that's
so
when
that means the damage, of course, damage rock is not working properly. So we need the purpose of a rock, there are a lot.
Okay, so let me interrupt a little bit, please. I think Nazma got frozen, but you can answer.
Better, resolution or.
Shahida, please let me interrupt. Forgive me for interrupting. We really appreciate everybody's. The topic that Nazma has presented. It got so much spontaneous response among the participants. That's very encouraging. So first of all, let us thank Dr. Nazma Ferdous for taking her time from her busy schedule to present this marvelous informative presentation. We learned a lot. And now let us open the floor for Q&A. My only request to you is that we welcome questions, but please make it a question. And also for the sake of managing the time, allow me to ask all of you one at a time to ask your question. And we'll request Dr. Ferdous to answer those questions. And then I will have one question at the end, but that's later. I see Asfar has raised hand, so let's start with Asfar. Go ahead, please.
Yes, Dr. Nazma, thank you. Simple question, like when you were referring to JWST and you had observation 1, 2, 3 sequential, you recommended that is the way to go. And if like one observation fails, you either like reprogram it or reschedule it, switching or skipping it or whatever. So how does this dynamically happen? So like this is on space. So is it self-corrective or it has to be corrected from the ground? Do you have any AI tool involved there? Just a light on this one. That's my question. Thanks.
It's a great question. Honestly, I did not know this answer until last week. It is AI on board. And unlike HST, again, it is very minute and second. This is in this orbit. This is when you're going to do this. And this is when you're going to do the science and so and so. In JWST, what they do is they send a series of observation at the same time. It's a pool that they send. And on board, it does have a self-correcting system. If something failed, pull the next one. It's not from the ground we are doing at this point.
Okay,
which
so
is I'll say a baby step in good right AI direction.
Yep.
Although it broke our system, but in the baby step. Yeah.
One of the thing I forgot to mention at the beginning that Dr. Ferdous' talk is a prelude to our another outstanding speaker that we have scheduled for September. He is the main architect of the James Webb Space Telescope. He's a Nobel laureate for his work, and he will be presenting us with similar webinar September 25th. So we'll send out that a note in due course of time. But again, Nazma has educated us probably a lot to prepare for listening to John Mather's lecture in September, which I had the opportunity to listen before. I do have a hardware question like Shahida had, but I'll wait until the end. Shahida probably has one more question, so let's listen from her so that she can finish her thoughts. Shahida, please. Please, Shahida, please finish your question. I don't know if she can now. Can you hear us? I guess not. Okay, let's move on. We'll come back to her again. If we can, I see Shabir Parvez Bhai is, she's an active participant in this area. So let's ask him to ask question, please. Unmute yourself, Shabir Bhai.
So Nazma, going to the operation, do people want you to point the satellite in inertially fixed rate, or do they often ask you to slew the satellite? And related question, when you're talking about moving the wheel during the MIRI, the wheel movement is going to move the satellite anyway. So what's your answer?
So where do we slew and often put into different direction? That is absolutely correct. You do have to slew.
But you slew during observation, in course of observation.
Observation has slew as well as science.
Okay.
Together, we're so and so doing engineering steps, calibration, slewing, and then you use the time for science where you are actually just looking at this. So that engineering has obviously slew, you have to acquire the guide star. There are a bunch of things that you need to do in that time first, and then just fix once you have that direction, you fix it in that direction and take the data on.
Okay.
Yeah, the slew is during the time period, as I mentioned in HST, it happened during alt occultation. But in this case, you're actually using time. So on this note, I will say, because you are actually use the actual time on the telescope for the slewing, we have to be very careful not to slew like really every which way. Try to, there is a huge, a heuristic. And prior to the JWST operation, when we were looking into for last 10 years, we have been developing. So one of the very big thing went into this, that you slew just slightly, as little as possible. Try to look at the same direction, just do as many things as you can. And JWST has this other thing, like every direction, every time you're looking, it is accumulating a little bit of momentum. And every third week, every 3 weeks, there is something called a momentum dump.
Unloading, You
have to unload using the onboard fuel.
Thrusters, right.
So idea was the slew and the momentum kind of went hand in hand, because momentum, if you know it's a vector, there can be positive as well as negative vector. You can actually have the telescope, if you have a way like you are really slewing like 180-degree opposite every time, then you actually will not acquire any momentum, but then you're wasting a lot of time.
Oh, so, no, I spend my lifetime as GNC expert, so I know all about that.
Right. So the idea was, the way we try to do is have a sinusoidal curve, right? Try just a little bit of slewing, try to accumulate somewhat, then try to slew it away from that direction.
Yeah.
Try
Yeah.
to unload as possible.
Unload
So
as
by
much
the
as you
time
can. Yeah.
you have to unload, you have to only have little, because I will mention that there's a onboard amount, like fixed amount of fuel that you are using to dump this excess momentum. And the little momentum you have to dump, you are actually extending the life of the
Yeah.
jet.
Yeah. Yeah.
So there
All
was
right.
a huge study that went, and we tried to, there was a huge, our main, what do I call, like a main preferences and main scheduling engine is really driven by that for
All right.
JWST. Try to slew just as little as possible, accumulate in one direction, then go
And then go back the other direction. Yeah.
and so and so. Yeah, that's what we did for this. There was another question, right? Was it?
Now it is tied in with the, you talked about the something spinning up for the Miri.
Oh, right. The Miri
Yeah.
is spinning up.
So
That's
spinning up itself is going to move the satellite, right?
right. So and then and that also creates momentum and so and so. So we try to like minimize that as much as possible, or minimize or try to correct it. In this wheel cases, because you go one direction for a while, again, it's a little bit of schematically scientific sinusoidal curve, if you will.
All right.
Go in one direction for a while.
And then you go the other.
And then go the other direction until you reach the limit, then go another direction. So and so try to correct each time.
Yeah. Okay.
That's the idea.
All right. Thank you.
Okay, so let's move on. Farooq Siddiq bhai, you have any question? Is muted.
No, I don't. Thank you.
Okay, wonderful. Shamsul Arifin bhai, you have been listening carefully. Any question?
Not so far, but I will try to understand first, and then if there is anything, then I can. Not
Okay,
now. Thank you.
Wonderful. And Musabir John bhai, any question? He's muted. Now we have Nasim Sajjad, who is an AI person in a different area. Nasim, Sajjad, you have any question?
Yes, I was so fascinating with that talk. Thank you so much. And my question was in computer science, we always are lacking with a subject matter expert. So let's say some people know AI and know computer science, and they want to learn more about this kind of network work. So those use cases and data source, can you give us some guideline about that?
That's actually an excellent question. Somebody should have answered me during my PhD, which, people did not. It is, I mean, I guess, one thing can be done. I mean, which as an immigrant, I don't know whether we can or not, but people, the kids who are born here really should be doing interning and other things. Because what happens is, these tend to be in academic, a lot of time when we are just learning AI, we are in an academic environment. In academic environment, so many times we are working with toy problems, just because the sheer amount of data, sheer amount of things that you need for your server. I mean, these astronomical data is a really large amount of data. It's very hard to really retool that for a academic purpose. You really have to come up with a smaller model of it to do that. But the memories are getting cheaper, the servers are getting cheaper. It's not like it cannot do it for sure. But in real life, when they're doing AI or all these things Google is doing, I think it just requires huge amount of data and a lot of coordination. Because what happens in an AI team, you may have a few graduate students, but you really need, for a real life problem to actually focus on the real life problem, you really have to have coordination from, state or whatever. Like I was looking into people who are working with AI tools for Medicare data and so. But it's a large amount of data. You really have to have coordination from state Medicare agencies or whatever it is. And, depending on who has the data, and what can you do, a lot of time, what can you do? We as an engineer, in our software mind, we have all this idea, oh, I'm going to do this cool thing, I'm going to do that. But so much is really driven by person who's driving the wheel, what that person, he or she wants to do, what the mission office is defining. So sometimes there is a bridge that needs to be crossed, and sometimes their perspective is very different from ours. And this has happened in my software engineering time, that I came up with all these tools that there was not exactly what they wanted. So and later on I realized that rather than me coming up with cool tool, I need to get into their head and understand what they want, because that's, unless you can write as many tools you want, if it's not used, not effective, it doesn't do anything. So you really have to understand people who are closer to that, whether it's a Medicare system problem or say the kind of thing Google at times is doing, trying to figure out the map and what's the closest business or so and so. You really have to see it from their point of view a lot of time. And your question is, how do I get there? I do not know. I think the best way, honestly, is to get in as intern or try to work part-time or something. I mean, academic ideas are great. When I started to work, and a lot of people told me that, why didn't I become a professor and so and so. The reason I really wanted my hand dirty in real life problem. Real life problems are done slightly differently, really by their, whoever is the stakeholder, by their, what they want, rather than what I want to do as a cool tool. Sometimes if you get enough trust from them, you have to build up that trust. Then you can, maybe you should use my cool tool, right? Otherwise, it doesn't, most of the time it's a little back and forth. You really have to create that trust. And how do you actually understand them? And how do you really actually tackle the problem? Unless you are really somehow related to the institute or related to that, I don't know how to do that. Honestly, some professors, I think, are probably much more attuned to trying to solve real life problem. I know there are people in UMBC here who are working with the Medicare, some are working with the school board system and so and so. And they try to get those data and try to work with their teachers, students to do it. I will tell you, when I did my PhD, since then things have progressed a lot. We could not have believed. We just didn't have the equipment. We didn't have the memory. Memories were very expensive to even think, to anything like that. Nowadays it's possible, but you probably have to want to choose a professors. I hope the computer science professors are starting to diversify themselves. When I did it, we are still working with toy problem. We were still like, we can do this cool thing. And really that is possible. And now in 20 years of time, what is not possible by computer science? What is not? Everything is possible. So I think we have to, the newer set of professors, a lot of us are dinosaurs, so we don't necessarily think that way. But the newer generation of professors I think, will be a lot more geared toward that. I hope educational institutes are going to be a lot more corresponding, a lot more connected with, where the real life problems in, and try to understand, what are they trying to solve. Some of the things, what they want can be underwhelming for you as an AI person. You're like, I could do so much more better. Why do they want it? But it is so much more important to get their point of view, get AI working on that. And it's only going to take baby step. A lot of us has too much stars in their eyes, and we think, this humanoid robot will come and do all kinds of things. Real life is a little bit more step by step. And hopefully, I don't know I'm answering your question right, but hopefully there will be more integration, where the real life problem is, and the professors or the student can actually think that you can do that. But a lot of it is imagination. A lot of it is practicality. You have to look at practical problem. And honestly, so many practical problem as a young person, like people who are doing PhDs, they tend to be younger and they are still not deep into practicality. So they don't really think of those practical problems. Like the school district problem, when I was young, I didn't have my children, I wouldn't have cared less. But it's a little bit of, maturing to, what the real life problem is. And it's not, I don't know, is that one answer? It has a lot of tentacles. I don't know whether I'm answering you right or not. But
yeah, my question was like, is there any public database for people to play around to use? I know like we can learn the use cases by reading the papers, but in biological science, they have a strict database and they can play
we have
around
too
with it.
many type of database. See, that's the thing. We have too many applications. Depending on what you're trying to do, I'm pretty sure there is. Like one example is the Zillow people. They just took the state database of all these houses and just fed into their system. They literally, that's that whole Zillow thing came out of that.
I was asking about those NASA thing you were doing.
Oh,
like
NASA thing.
research
On NASA
you are
thing,
doing,
I
is there
will
public
say,
database for that?
on the NASA thing, I will say is NASA is not, I will say they're taking baby step when it comes to software. They're very apprehensive about like onboard AI. They only take baby step. STScI is an exceptional case because it's astronomical science. They really allow a lot more freedom and openness to it. Whereas other NASA application where, say, particularly a mission and hardware and so, some secrets are there and so, they're not as open. You don't really get access to that very easily. STScI, I can see people can just look into this astronomical data and come up with patterns of galaxies, come up with so many AI can be used on that, right? Come up with this thing and actually discover something people did not discover. It's a lot of data mining that can happen. So our institute's case, actually, there is an archive. You can just ask for it. You can go into STScI website and there's a data archive and there's a process to ask for data. You can get any data you want. Okay. And the thing is, whereas there is AI application of data mining there, that hasn't come, that nobody yet asked for it, you know what I mean? Yeah. But other NASA cases, they tend to be a lot more restricted than us. So I would say, rather than NASA, I mean, look at planet Earth. NASA's idea is looking at outside. Planet Earth definitely has a lot of, planet Earth is my favorite planet, by the way. And it has a lot of AI that can be done on regular people's life, real people's real application, and so. And those are the ones that will actually quickly get into fruition, quickly, evolve and develop. So I would say, NASA is not, NASA's AI is, NASA is big into coming up with spectacular hardware or something nobody else has done. Software, when they are like, okay, slow, that's not their legacy, I would say. They're making progress. It's a very good agency, but when it comes to AI, they're a lot shy. There are other agencies like, for instance, National Oceanographic Agency. I think there's a lot of data mining, a lot of things that can be done. They are probably a little bit more public with their data.
Yeah, thank you.
Sorry. I mean, this is a, this is
so
something
allow
with
me
a lot
to
of
break in as far as imaging, and this is very interesting discussion. And thanks, Sajjad, for the questions, and thanks, Nazma, for all the answers. We surely are learning a lot. But as far as imaging is concerned, so I had a brief discussion with Meta as well about this. So the diffraction limit, which is what the crux of the matter. So in the middle of the space, you have this antenna or the mirrors. that light is being reflected and you are illuminating all the lights except you are collecting IR.
Right.
IR technology is not new, it's very old technology.
Right.
And then that IR CCD or whatever is in there, making the image and transmitting it to the Earth. As
Right.
simple, but it's not as simple, of course.
Right.
Now, the thing is that why, I mean, as a small researcher, we use far infrared, or as we call terahertz radiation.
Right.
And there's no CCD as of yet that can image in that spectrum. So we have a technology of cameraless imaging with lattice resolution. So resolution has to be overcome because of the diffraction limits. So we found a way of overcoming the diffraction limit.
Yeah.
And I tried to ask these questions a lot of people, and actually Mehta has my paper. He forwarded it to his colleagues without getting any response from anyone. Do you envision that NASA or your institution might be benefited with this kind of imaging technology?
I am pretty sure they would. And I am pretty sure there are other people who would ask for it. This is not my area of expertise, so I cannot quite tell you for sure. But NASA is still not, what do I say? They tend to use their own technology a lot more. You know, they are not trying to use technology from outside. They can be a little bit more like not engaging in that process, if I say so, you know. But if there is a good, good technology, there are enough thing about it, you can try to go and explain to them, you know, this is what we have, and maybe for next things, because, you know, next telescopes are all gonna be infrared, more or less, because the more we learn, more we are gonna try to see the age of universe. And if you're gonna see the age of universe, that's what you have to do. You have to do infrared. Like HST, for instance, actually had visible, ultraviolet, and many things. JWST became mostly infrared because that's what we are trying to do. So it's possible, you know, they will need it, and or some component of it that will be helpful for them.
No, I understand. I understand the scientific issue is that that's the one we are dealing here with. So, but I mean, again, I have dialogue with some other people. IR is a very narrow band of spectrum. So, because the sensitivity issues, IR is more sensitive than visible or even UV, etc. But far IR is even more sensitive. Terahertz is even more sensitive, which is what we use. And then by that, what they could discover, they don't know. I mean, IR is the treasure chest, as Mehta will be talking about. That's the title of his topic, opening the IR treasure chest. So then the point is that, like you said, NASA is very selective. Although they have some SBIR and that kind of program, but that's peripheral. That's not their main thrust. They always depend on what they are doing in-house. So as when it comes to this NIH syndrome, meaning not invented here syndrome, NASA is definitely a champion of that.
There is an inertia, and it has to be. See, you know, the thing is, it's a public money, and many of NASA's thing is really for the food for our, you know, brain and food for our soul, and not directly, at least at immediately, no commercial purpose to it. So you are really relying on public money for tax money. You have to give people back. You know, it has to come in spectacular fashion. Otherwise, why would somebody use that kind of money? You know, unless we actually have the taxpayers in US. And although this was an international project, almost all of it was US taxpayers who paid that $10 billion, right? Nobody else is paying. So we have to be, they have to be very guarded. If anything goes, I mean, I'll just give this small, story. I don't know, many of you may not know, when HST first went on, HST had all this promise and so, they're going to do this and that. Oh, the telescope is going on to the space. Oh, spectacular. Turns out they had a very small aberration in the primary mirror. And the image came out blurred. Although image came out blurred, it was way better than any other image the ground-based telescopes were going to get. But everybody was crestfallen by this very small aberration. And from what I hear, people in the institute could not say they work for HST. They were so shamed. And then, the astronauts went on and actually put something called a coaster, another thing that actually made the correction of that aberration, and that spectacular image came in. If JWST had many things they had done for the first time, if they did not produce, and this $10 billion they spent, the people would be shaming the whole science community. So they are very, very conservative on what they can do. They have to be. It's a lot of responsibility on them. And if one telescope doesn't work, next telescope is going to be another 20, 30 years. And they are hungry for more knowledge, more things. So I understand the mindset they're coming from. And that's why I say a lot of scientific things, a lot of, like, at least computer science wise, that is very true. It is so much easier to experiment in planet Earth because, something like Tesla or whatever, some self-driving car actually did a crash. So what? You are going to change the software and do it. If space you crash, that's it. That's it.
Yeah.
So Hubble, for instance, few days back, what happened is they have a side A and side B for their circuits. And some reason side A stopped working after 30 years. So they were switching to side B, or the other way, like side B was working. Just to switch that, they brought in all this expert because one single mistake.
Right.
Done.
Yeah.
So you have to be careful.
We have Shahida raised hand and Asfa raised hand. So let's go to Shahida again. Please go ahead, Shahida.
Actually, most of the discussion we have already covered, but only the data purpose, actually what I know so far recently, NASA satellite data, raw data, is very useful for the student. So I'm telling you about the raw data, I think that's easy to retrieve also, NASA from NASA through the institute. And another one is a national lab. And we all know it, but the purpose, whoever asks the question, where can she get it? You get it. National lab, one of the resource, and National Science Foundation, research under National Science Foundation, also very, very helpful there, providing data. So privately, National Science Foundation also very helpful to get the data from the private sector. That's actually I want to add.
Thank you
so much.
Yeah.
Yeah, Aspa, please.
Yes, same thing from the discussions. Many parts of my question has been answered already. Like my question was, like you are mostly involved in data collection aspects, but after that, there's a whole lot of things before the data means anything to anybody. So like I was asking, like, what types of storage, and you said it can be many types, right? So as Anis Bhai was saying that, is infrared images and all that new technologies, but still it's a huge amount of data. Like each observations itself could be huge, and then so many observations coming in every second. So storage was a big question mark. Then how do you process these? Like for making any meaning, it has to be on like some classification models like CNNs, and there's so many other ways. And then comes the analysis and all. And then, so storage wise and processing wise, the quantum technology is, already coming up. It's already available by IBM. But the next 5 years, you will see a huge rise. So this definitely is a prospect for NASA, and I'm sure they're already researching on it. So you are in close communication with the engineering team and all. So what do you think they are, how far they are into quantum technology and quantum data modeling? I mean, QML, quantum machine learning aspects.
I would probably say not as close, but up until now, I mean, as you mentioned, rightly mentioned that it's a lot of data. Up until now, the archive and everything was actually in-house. They're definitely realizing this limit to it. And, you know, the amount of data is literally even heating up the institute. It's that much. So they are closely looking at clouds and Amazon, this and that, the outside vendor. This is the first time I'm really seeing like they're starting to, you know, let's do, you know, take outside help on certain things. And I'm just strictly talking about our institute. I don't know about the other NASA facilities, but definitely there is openness, at least when this storage comes in, because it's only gonna change, you know, Murphy's law. It's only going to increase by 2, you know, every time, and it's too much to handle. So they are definitely, at least the cloud and stuff, they are starting to do that. Now, I would imagine a lot of this quantum storage thing you are saying, in my head, you know, it is likely big players in technology like Amazon or Google, they are probably going to do it first. And NASA is going to probably use it. Because as I said, the software side of it, you really have to have a huge research team to be able to do that. And NASA's main focus tend to actually come up with a lot of these hardware things. Only, you know, the software is kind of a, what do I say, more of a foil at this point, you know, and which may change, but it's not, that's the state right now. In STScI, we are very lucky that we actually get to use software a lot more. And that's the reason is most of the NASA mission doesn't go on for 30 years. The HST is going on for 30 years, still going. JWST is hopefully going to go another 20 years or so, because the length of the project is so much. And that's where software can really enhance it. And that's why they've put a lot of buck into that. Rest of them tend to be, you know, if you look at the Mars mission and so, idea is, okay, land, that's the big thing without trouble. Stay there, collect a few things, send us back, you know. They're trying not to do as much automation. There was some automation that was done on the rover, try to not hit the rock and so. But the software is not their biggest thing. I would imagine those big players in Silicon Valleys and, you know, Seattle's and other places, they are the one who will probably headline it first, implement it, and NASA at that point will probably outsource, I would imagine, because as far as big data goes, there's nothing bigger than astronomical data, that's for sure, right? And that will be a huge, huge, you know, good usage of that application. We are starting to, you know, the institute is really starting to train people as far as Amazon cloud-based stuff goes, and so. So eventually, I can see in 5-10 years it might move.
Yeah.
Move at least the storage.
Yeah, thank you.
Yeah, so to ask first point,
Yeah.
let me just interject one thing. So
Yeah.
quantum computing is good for computing, and
Right.
NASA's issue is storage.
Right. Correct.
So,
We are talking storage at this point, not computing.
So there is no computation need. NASA could resort to quantum computer. But yeah, you were saying something else, but please go ahead.
Yeah, I just wanted to say that what mentioning to everybody that IBM quantum is leading the quantum world now. You mentioned Google and Amazon, but
Right.
IBM is come back again with this.
Right. I mean, yeah, I should have said IBM has done great work. You know, I mean, every time I think about the whole state of solid state. Shockley, you know, he came up with the first transistor.
Yeah.
You cannot beat him. So, I mean, IBM led, you know, of course, the whole mainframe and so and so. So my point was not just, what I'm saying is the private sector is probably gonna
right.
take that
Anish
up.
bhai as well, it's not only for data storage. Sorry to interrupt. I mean, the quantum computers, of course, you know, is like 30 times or maybe more, like
More.
3 seconds versus
Yeah,
30
yeah, yeah.
years.
Yeah.
So it's definitely
It's a computation, and
yeah.
NASA's issue is the image processing, which is a because I myself is involved in a lot of imaging technology.
Mhm.
So I kind of feel, and I'm also connected with quantum computer work, not directly but indirectly. So the quantum computer that Google came up with, IBM is what, 16 qubit or 32 qubit they are talking about now. So
60.
Google is planning 256 qubit pretty soon. And once that kind of computation is mind-boggling capabilities of computation,
Right.
not storage. So that is
Yeah,
the
yeah.
difference I want to make.
Got it.
I will mention that when it comes to computing, you know, we have talked about whether some of our software can use like commercial product. We have tried the feasibility of it, what can we do, and so, because essentially what we are doing, this optimization scheduling, I mean, that's the very basic computer science, and you do that kind of optimization scheduling in so many other domains, right? So it turned out that for us, because you are really talking about these observation constraints and the agility at which we have to certain time look into and really solve the problem, because this observation planning is a somewhat unique problem in some ways. There is a baseline of basic AI, but it's also a somewhat unique problem, and it's not as commercial. Right. So for us, doing the in-house, at least come up with the software would be easier. Now, much easier rather than using commercial product. But software is one thing, and using that software to do actual computing is a different story. And that might happen. That definitely might happen. And when the computer became very fast, the nature of software and computing also changes, which is a very interesting thing. You know, during my time when I studied computer science, we were so into heuristic, trying to manage the memory, try to make it as fast as possible with our very limited slow computer. You know, we didn't have much room. That's how we were taught. Nowadays, simulate everything. Figure out what's the best. You have so it's moving from heuristic driven one result to simulate what you can and then figure out what's the best result. So our nature of software probably will change once that kind of computing will be available to us. Computing power will be, I can see that's happening, but it's gonna be NASA is almost always, when it comes to this 20, not 20, but 10, 15 years behind. I'm pretty sure the other application in, so-called commercial application and stuff will probably jump into this faster and actually make it. NASA only goes there once you have certain amount of confidence, which would happen when you have a lot of real life application doing it and turns out it's just fine. That's when I can see it's happening.
So simulation is actually another thing, which is simulation is always based on what is known.
That is true. That is true.
Simulation can never invent something new. For example, if someone had to simulate the Higgs boson,
no,
it's not possible.
No.
So similarly, many other things that NASA is involved just cannot be simulated, No,
it cannot be fully. I mean, it has to start with the knowledge. But, what I'm saying is earlier, the state of computer science was, you obviously started with knowledge, but you are really directing every step of the way by your heuristic and searching. Just because you have this huge search tree, you cannot
It's more
search
of a
everything.
design of experiment as
Right.
opposed to simulation.
Correct.
Simulation is a good teaching tool.
It's a good teaching tool, but
Teaching tool.
earlier that tool was not possible. You know what I mean? We just did not have the state of hardware that would allow us. Right now it does.
Exactly right. Well, if anyone has any more questions, please feel free to ask. If not, I will ask Nazma to say a few words in closing before we formally close it.
Oh, thank you so much for inviting me. I felt very honored. I don't know whether I answered the question, and it looks like most of the people here are not exactly software engineer. I gave a very software engineering talk that may not have resonated with you, but that's the only thing I know, really. So I try to, say what I did. Hopefully you got at least some glimpse of it. I will say that the JWST launch and the euphoria it created made me feel like my work of 20 years was worth it. I was very happy how it reached many corners of the world, including my home country, Bangladesh. People were so happy. The kids were really looking at glazed eyes and really looking at beautiful science images and so and so. And I will tell you, even in the institute, we never believed it would be this good. The images were spectacular, and unless you actually take the image, you never know how good and what scientific value is it. And I understand it actually also has a lot of scientific value. So thank you for being, part of my what do I say, gratitude and happiness in being part of this spectacular process, a spectacular telescope. We say a lot of time, the Galileo changed the path of astronomy, then Hubble came, and I think JWST would again take it like many, many steps further. Thank you so much.
Well, we could not be prouder for many reasons. One of the main reasons is Nazma is one of ours. And she is the leading software engineer, scientist working for such a noble organization and cause, and great science coming out. And she is part of that. We couldn't be prouder as a fellow Bangladeshi American. So with that, again, our thank and gratitude on behalf of AABEA, let me express our thanks and gratitudes to Nazma for her time, for her deliberation and educating us on so many things. And this is just the beginning. I'm sure next time Nazma will bring more knowledge base and more wonderful information to us in another session. With that, let us say goodbye for today. Thank you all.
Thank you.
See you next time again. Bye-bye.
Thank you.